In this lesson, we'll discuss the relationship between power and energy. By the end of the lesson, you'll be able to define power and energy as units of measure, calculate power and energy using voltage, current, and time, and interpret the instantaneous electrical measurements and time of use electrical measurements. So why is this important? Let's look at a real-life scenario. Look at an electrical input of any appliance. It either has a power rating listed as some number with a W next to it, or a current and voltage rating. Well, what do those mean? And how do we assess what they mean for electrical needs? And how do we determine the appropriate solar panel system that would fit the needs of a specific device or maybe a whole building? Let's start by looking at the unit of power. Power is typically defined in watts or kilowatts. Kilo is the SI notation meaning 1,000. Power is the rate of doing work or rate at which energy is used, produced, or transferred. More simply, power is just energy divided by time, and a common unit is W, or watts. What can we do with this unit? In a previous lesson on efficiency, we looked at power calculations. Again, watts can be calculated as voltage multiplied by current flow, or amps. The watt is also the primary unit of power measurement used in all electrical systems, including photovoltaics. As an example, you might look at a clothes dryer which operates at 220 volts and 8 amps. So we can calculate the power by multiplying 220 volts by 8 amps, which equals 1,760 watts when in use. Another example would be a photovoltaic panel which operates or outputs 40 volts at 5 amps. Multiplying those together, we would get 200 watts when operating. A third example, which just moves around the variables, would be to say look at a whole photovoltaic string, which would be just several photovoltaic modules wired in series. If that system produces 1,300 watts and outputs 224 volts, divide those by each other, we can then figure out that the current flowing through the system is 8.03 amps. So there are 3 different ways that we can calculate power. Now let's look at what power has to do with energy. Well, as we just saw, power is defined as energy divided by time. So energy is power multiplied by time. Energy includes how long a device is being used or how long it's producing power. There are many units for energy, such as watt hours, kilowatt hours, BTUs, which stand for British Thermal Units, joules, and calories. Calories also happen to be the same energy unit that we use to describe foods and burning of calories. Energy for electricity is typically measured in kilowatt hours or watt hours when being consumed or produced. Coincidentally, sunlight energy is also measured in kilowatt hours or watt hours. Knowing this, we can compare the sun's energy output to photovoltaic energy and electrical load, or the demand, using this common unit of kilowatt hours or watt hours. It's a direct comparison. So how do we use that energy value? Well, again, since energy is just power multiplied by time, we can look at everyday appliances like, say, a hairdryer or a light bulb. In the case of a hairdryer, it might use 1,100 watts when it's on. Well, let's assume it's on for 15 minutes per day or 1/4 of an hour, and using that 1,100 watts. One might use that same hairdryer for about 180 days per year. So we can then multiply the 1,100 watts by the 1/4 of an hour, or 0.25 hours, by the 180 days that it's in use per year. That means that the hairdryer consumes 49,500 watt hours, or 49.5 kilowatt hours per year. That power value might seem high, 1,100 watts. So let's compare it to something which consumes a little bit less power, like a light bulb. If we take a 60-watt light bulb and use it for 4 hours a day, and just about every day of the year, say 345 days, we would multiply the 60 watts of the light bulb by the 4 hours of use per day, multiplied by the 345 days per year. That equals 82,000 800 watt hours or 82.8 kilowatt hours. So even though the light bulb has a lower power rating of only 60 watts, it consumes much more energy over the course of the entire year. So that's why power and energy are both very important units. The power tells us about the instantaneous consumption, and the energy tells us how long that electricity is being used or produced. So the important value that's needed for energy is always going to be time. How long something is going to be used or how long it's producing that power. So why is this all important? Well, a solar module can produce a specific amount of power based on sunlight levels, and that amount of power varies constantly based upon weather and seasons and day or night cycles. Because that power level varies, the only way to know how much electricity is produced during a year is to calculate the sunlight power over time. That's energy. Energy values can be summed over a time period to get the total energy used or produced. This helps us compare the energy demand to the energy production. So how do we put this all together? Well, let's look at a few examples. First, let's look at a photovoltaic module that produces 38 volts and 5.68 amps under full sunlight conditions. If we multiply the voltage of 38 volts times the current produced, 5.68 amps, we get 215.8 watts. If it does this for an average of 4 hours per day, we multiply the 215.8 watts by the 4 hours, and it would produce 863 watt hours per day. And if it does that for 365 days per year, we multiply the 863 watt hours times the 365 days per year, and it produces 315,126 watt hours or 315 kilowatt hours. Our next challenge is to figure out precisely how much energy is actually hitting the Earth's surface so we can collect and convert that solar energy into solar electricity. That's going to be in future lessons on figuring out this actual sunlight level or insolation value. So now you should be able to define power and energy so you can then calculate that power and energy using voltage, current, and time measurements, and interpret the difference between instantaneous time measurements for power and time of use measurements for energy. We're going to examine a few ways to evaluate the energy consumption of different electrical devices and develop an energy audit. First, we're going to start by using appliance labels, then use other methods to determine power and energy consumption using empirical measurements, then look at online resources, an electrical utility bill, and how to conduct an energy audit of electrical devices. Nearly all electrical devices in the United States come with a label or a tag that indicates the amount of power the device consumes or the voltage and the current required to power the device. If the device power is listed on the label, we can calculate the energy by simply multiplying the power of the device by the number of hours the device is in use. So, for example, a 60-watt light bulb that's used for 5 hours per day would use 300 watt hours per day. And if it's used by 365 days per year, it would consume 109,500 watt hours per year, or 109.5 kilowatt hours per year. Separately, if a light bulb indicated that it used 0.5 amps while operating at 120 volts, we would then calculate that it consumes 60 watts when in use. We can then multiply the power by the hours in use and again derive the energy consumption per day or per year. Depending on what type of label is shown on a device, you'll have to perform one of these two calculations. Let's now look at this in real time. In this example, I've plugged in my light bulb into a watt meter, which shows the system voltage is approximately 120 volts, but since it's off, there is no current, or 0 amps. Once I turn on the light bulb, the current measures 0.509 amps. It also tells me that the wattage of the system is 67.7 watts, which is close to the calculated value within error. I can then use the same meter to compare 3 different light bulbs: an incandescent, a compact fluorescent, and an LED. And we can see that for almost the same equivalent brightness, the incandescent bulb uses 67 watts, the compact fluorescent uses 19.5 watts, and the LED uses 8.5 watts. This also illustrates how switching to more efficient devices can reduce the overall energy consumption. A coffee maker is a typically high-powered device, and the label indicates that it consumes 7.5 amps when in use, plugged into our watt meter. So we can see that the background power is about 0.5 watts, but as soon as we turn on the power, it goes up to 873 watts. 120 volt operating system voltage times 7.5 amperes equals 900 watts. So the coffee pot is operating near its maximum rating. Similarly, a microwave, which is rated at 13 amps, has some background power of about 1.5 watts, and then goes much higher to 1,691 watts when in use. Finally, a refrigerator is a bit more tricky because while there's an amperage rating on the refrigerator, it cycles on and off with the compressor, as well as when the light goes on and off with the door open. So it goes very low when the light is off, and then it goes slightly higher when the incandescent light bulb turns on and the door is open, to 94.5 watts. The power then goes much higher to 880 watts at the peak power with the compressor running. So the power consumption is very variable. In this case, an instantaneous power measurement like we did before is not very informative because consumption fluctuates so much. In situations like these, finding published annual energy consumption data from the manufacturer or a third-party site like Energy Star would be more accurate. We'll look at how to do this in an upcoming segment.
There may be some situations where you cannot directly measure the electrical usage of the device, or you cannot find the product label for the device. In that case, a manufacturer's website or even the Energy Star website might be able to provide some information for you about electrical loads. So I'm at the EnergyStar.gov website, and this lists all products that are Energy Star certified, meaning low energy consumption. This is how we'd begin to look at load for a device that may have variable conditions like a refrigerator or something that you just can't find a label for. So if I click on refrigerator and go to the product finder, it will take me to a list of different manufacturers' devices and the energy consumption of those devices. So you can look at those devices and you can narrow them down by brand. And once you've narrowed them down by brand, you easily can see what the energy use is going to be. It's an approximation, but this Maytag refrigerator, for example, would consume 469 kilowatt hours per year of electricity. So if we divide that out by 12 months, we would see what the energy usage is per month or by day by 365. But we would put this into our balance sheet looking at the load usage of light bulbs, refrigerators, microwaves, clothes dryers, any other electrical device that you might have in a home or a building. So from there, we can use any of these three pieces, the direct measurement, the load listing, or something like a manufacturer website or Energy Star site to be able to look at what the total load usage is of all our devices and get closer to an understanding of what is consuming electricity in our buildings. Now that we've looked at how to assess individual energy loads for devices, we can look at an energy load for a whole building. And the easiest way to do that is to simply look at a utility bill. If one is working off-grid, meaning not connected to an electrical grid, you won't have a utility bill most likely. But if you do have on-grid connections, you will have a utility bill. Even if it's minimal, you'll have an idea of what your electrical usage is. So let's take a look at one of these electrical bills. Now this is one from a local electrical supplier in upstate New York, although also a national provider. And there are a few things that are listed in here I want to point your attention to. One is that there is a bill for both electric service and gas service because this utility provider provides both. However, we're just going to be looking at electric service, knowing that this home does not use electric service for heat and uses gas service for heat. So one of the important pieces is not necessarily the dollar values here, but it's the electric usage history. Notice that the units are in kilowatt hours. So we have a usage of energy for each month, and they show historically how much energy is being used each month. So if we want to get an overall electric energy usage for the year, we could sum each of those months individually within the bill to get an idea of what the annual energy usage is going to look like. But we see trends for June and July and August being higher for electricity, slightly lower in November and December as air conditioning gets turned off, and then goes up again in January and February, most likely because of the fans and blower units within actually the heating devices in the home. But you get an idea of what the overall energy usage is. Numerically, this is a little bit easier to see. If we scroll down the bill a little bit more, we can actually see the values here. So you can look at it graphically or by value, and it's much easier to simply take these numbers, sum them together, and get an annual energy usage. So as we begin to plan for a photovoltaic system, we take that total energy usage and know that that's our annual load, and we would build off of that to be able to look at the annual use. So let's take a look at that now. I've taken the monthly energy usages and put them into a spreadsheet program. The spreadsheet, I've taken the data and also put them into a graphical format, which lists it chronologically from January to December. So this is slightly different than the bill, where it shows it on a rolling basis from month to month. What we can then do is easily calculate our annual energy usage by just summing all of the values within the year. So I'm going to use the sum function, and I'm going to highlight from May and going backwards to June, not including the previous May. So I have a 12-month span, and so by highlighting all those values, I get an energy value usage of 10,753 kilowatt hours. So that tells me that if I was to want to replace all of my energy usage with photovoltaics, I need a photovoltaic system that would produce 10,753 kilowatt hours. Now that we've looked at how to calculate the annual energy usage, again, we can go back and look at a monthly energy usage like 638 kilowatt hours. Monthly usages may be important if you're looking at short-term use or working off-grid where batteries are important. It's important to know what your monthly usage is going to be, or if you're trying to deliver electrical service for only certain parts of the year. So, in summary, we've looked at how to use the energy bill to calculate the monthly and annual energy usages, and next we'll look at how to take those energy loads, those usages, and convert them to figuring out how many photovoltaic panels we might need to supply that load.